Okay, this is just an example problem using the method of characteristics again to solve, well, in this case, it's a second order linear partial differential equation. But you will see that, actually this method comes up, in many other contexts. And the way that it arises this time is that if we first Fourier transform this second order partial differential equation, which describes a shear flow in a two-dimensional space. That is, a third dimension of this fluid is an infinite expanse with boundary conditions that make it not matter. So we've got time x and y again in this problem, but now we've got this diffusion term, this viscous dissipation term here in the middle. Okay, so what's going to happen after we Fourier transform x and y out of this equation and get instead kx and ky, which are the Fourier transform variables that I'm going to use. We're going to end up with an equation that is actually first order and linear in kx, ky, and time. Okay, so that will then be something that we can solve with a method of characteristics problem. And you can see that on the exam, just in case some of you guys watching are a little nervous, that I do guide you through on the exam how to do those transformations to get an equation that you can solve. So let's go ahead and just imagine that we were starting here and we wanted to do this Fourier transformation, and that's something that will come up later in the course, so don't worry if you don't understand how those work yet. But what you would get if you did everything correctly is a first order linear partial differential equation in new variables t, ky, and kx. Okay, so you see here there's ky and kx terms appearing in the equation. Okay, so this c hat is the Fourier transform of the original variable, the original unknown variable c. And so we can recognize in this equation that I've got a term that's proportional to c and two terms that involve first partial derivatives of c hat. Okay, so we're going to group those two terms together. And just like our plug flow equation, those are the terms that we want to group by doing a change of variables. We want to collapse these two independent variables into one, namely tau. Okay, so this is the idea. So we have the derivative of c hat with respect to tau is equal to the two first order partial derivative terms that appear in my PDE, and those, after I move the c hat term over to the other side, are just going to be equal to minus k squared diffusion coefficient times c. Okay, so now we have expanding all of this out, we recognize that what this equation really says, if I want this to be true, then I have to think about what is the derivative of c hat with respect to a new variable tau. And if I do that expansion, I've got dc hat dt, dt d tau, and I've got dc hat dkx, dkx d tau, dc hat dky, dky d tau. The only way to make this total derivative expression, this general expression, be the same as the equality here is to choose that dt d tau is equal to 1. That is, the coefficient on this term is 1. The coefficient on this term should be 0. Okay, that is to say that in the original problem that we have here, we see that there is no dk dc dkx term, and that's why we're choosing this term to be equal to 0. Okay, and we also have dky d tau should be the minus lambda kx. Okay, so that's this coefficient right here. Okay, so that's the way this correspondence works. And now we're going to solve each of these three ordinary differential equations. And we get that t should be tau with some undetermined coefficient. The new variables that we're introducing, so the original Fourier transform variables were kx, ky, and t. And now we're going to have tau, qx, and qy, which are going to correspond to those things. So we have t, tau, and we have undetermined coefficient here that comes from the tau equation. And each of these things can be solved in similar fashion. Ky just gives us the minus lambda kx times tau plus undetermined coefficient that's going to, again, depend on qx and qy. And this equation is the easiest one to solve, of course. It just says that kx is some constant in tau, but it can depend on the qx and the qy terms, okay? So we don't want to forget that. All right, so now what are we gonna do with this? We're going to require that these two coordinate systems coincide at for the initial data. That is, when t is equal to 0, tau should also be equal to 0. And so the nature of the solutions here then specify that for that to be true, for these two things to coincide at t equals 0 and tau equals 0, this coefficient has to be 0, which says that t has to be equal to tau for all time. And the other ones, when I plug in tau equals 0, we find that ky should be equal to the undetermined coefficient here. So ky is some function of qx and qy. And kx is also that function of qx and qy. It's a different one, actually. It comes from the x equation. And that says that you have qy is ky plus lambda kx times t, and qx is just equal to kx. Okay, so notice this now is the correspondence. This is going from the original Fourier transform variables on the right to the new method of characteristics variables on the left. Okay? So by construction, what we've done is we've collapsed our partial differential equation into this object. It's the derivative of c hat with respect to tau is minus k squared d c hat. Okay? So you might think, based on the things that we were doing the other day, in fact, it may be kind of suggestive that this k squared looks like a constant, and I can just immediately integrate this thing with respect to time and find that c hat is c hat at the initial time e to the minus k squared dt, d tau. But remember, we are now working in coordinates tau, qx, and qy, not tau, kx, and ky. And in those new coordinates, k squared is a function of tau, okay? So you can see that k squared is a function of tau because if you go back to this equation and you isolate kx squared plus ky squared, which would be the k squared here, that's what we mean by k squared, then you would find that this is qx squared plus some qy squared plus 2 lambda kx t qy, and then there would be a t squared term. And so the t squareds and the t factors that are popping up inside k are really depending on tau because tau and t are the same. Okay, so that's just a word of warning that, you know, don't forget what your coordinates actually mean in these problems. So this is the actual expression for k squared. It's just that thing that I just described. If I'd known it was coming, I wouldn't have described it. And so what we're going to do is to solve it with this dependence on tau built into the equation. So it's a much more complicated ODE to solve, but it's still a separable ODE that can be written down and integrated directly. And so you have, at the end of doing that, you have the log of c hat over c hat for the initial tau equals 0 c hat is always equal to this complicated function of tau. Okay, so it's a polynomial, third order polynomial in tau, and that comes from the integration. Okay, so we started out with second order in tau and integrated to get third order in tau. So you guys can all do this, but you just want to be careful not to make this mistake in that very first stage. Okay, so everything from here is basically the same as the problems that we were doing. It's just much more complicated. Okay, so we have that c hat is equal to c hat when tau equals 0 times an exponential of minus d tau multiplied by all of this stuff. Okay, so what happens when I let tau be equal to 0? Then we get our initial conditions back, right? So all of this stuff is going to vanish. And we have to consider the Fourier transform of the initial condition. Let's go back and look at what that initial condition was. We said that we had a point pulse of whatever species is diffusing in this shear flow and that's a product of two delta functions, delta at x and delta of y, says that we've got a pulse at location x equals y equals 0. And so those delta functions can be Fourier transformed pretty easily. And the rest of this is really not a method of characteristics problem. But because you guys know something about delta functions after the first couple of lectures, let's go ahead and say briefly how you do this. So the Fourier transform of any function, so this is the function that I'm Fourier transforming, in two dimensions is e to the minus ikx, e to the minus iky, y. And we have an integral over x and y. Those are the original variables, x and y. We're integrating this kernel with the delta of x and the delta of y terms here. That's my function that I'm Fourier transforming. And you guys know how this will behave, right? So I'm integrating something multiplied by delta functions here. And that something, when I let x and y both be equal to 0, which is where the argument of these delta functions goes to 0, this thing is just going to become 1. And so the Fourier transform in this case is just 1 over 2 pi. Okay? So even though you guys don't know anything about Fourier transforms yet, if you looked up the formula in a book, you could use what you know about delta functions to complete the Fourier transform in this case. All right. So we are almost done. We now have the solution in Q space. So C hat is C naught, which is just 1 over 2 pi, multiplied by this exponential, where the argument of the exponential depends on tau, qx, qy, in this complicated polynomial function in here. Okay, so now if you wanted to map this back to K space, you would remember that qx is related, qx and qy are related to kx and ky through the characteristic coordinates that we derived. Okay, so that says that everything in curly brackets here can be pretty easily rewritten to change coordinates back to t, kx, and ky. And now you have the solution to the Fourier transformed problem, right? So this is C hat of kx, ky, and t is 1 over 2 pi exponential of all of this stuff. So now your solution is written in terms of kx, ky, and t. Okay? So, you know, it's now quite complicated, but Mathematica can do it, to go back and do the inverse Fourier transform to go from the solution in kx, ky, and t back to the solution in x, y, and t. Okay? So there's a lot of steps in this problem. First, we had a partial differential equation in x, y, and t. It was second order. We converted it to a first order partial differential equation by doing a Fourier transform. The Fourier transform left us with a first order PDE in kx, ky, and t. We solved the first order partial differential equation by the method of characteristics. We found the solution in characteristic coordinates qx, qy, and tau. We inverted our coordinate system to get back to the solution of the Fourier transformed problem. That is the thing in a box here. That is a solution in terms of kx, ky, and t. And now the last step is to invert the Fourier transform and recover the solution in x, y, and t. Okay? So Mathematica, I mentioned, can do this, and the inverse Fourier transform comes out to be this expression here, which can be slightly simplified to give you this final answer. C of x, y, and t is looks like, you know, something like your usual diffusion Green's function, 1 over 2 pi dt. But you'll notice that the solutions now are not spreading in a spherical way; they're spreading in a skewed way because this was a shear flow. Okay, so that's really what's described by this complicated thing that depends on the degree of the shear rate lambda. So if you look back at the solutions, you see that for different shear rates, that degree of skew is getting larger and larger. And so I think that's where we'll stop here.